So I'm going to talk about nonlinear internal waves and try to illustrate that it's a very rich area. So lots of interesting sort of nonlinear behavior. So maybe first of all, what are internal waves for those of you who are not familiar with them? So everything I'm going to talk about will be in two dimensions in the vertical plane. So this slide illustrates the colors, illustrate the density field. So you've got light fluid overlying dense fluid. In this case, there's a layer called the pycnocline where the density varies. Okay, so in this case, you could model it as a two-layer fluid, but as I'll illustrate, more complicated stratifications are much more interesting in terms of nonlinear waves. Okay, and so we've got gravity acting down, and the gravitational restoring forces acting on the vertically displaced fluid are what drive the waves. So here I've perturbed the pycnocline. It's pushed down in the center. It's being pushed up to either side, right? And if we release it, you see you've got several waves propagating away. And the leading waves are mode 1 solitary waves. So mode 1 refers to the fact that the fluid is displaced vertically in the same direction at all heights, right? So from top to bottom, right, the fluid is being displaced downward. Behind this leading wave, right, it's being displaced upward. So, and then several trailing smaller waves are also mode 1 waves. You can also see a small mode 2 wave here where, so mode 2, say fluid sort of above the center of the pycnocline is being raised and fluid below is being pushed down. So fluid being displaced in opposite directions. And then mode 3 waves, you'd have, up, or down, down displacements and so on. Okay, now because this stratification has a thin, relatively thin pycnocline, most of the waves, you think of they're propagating horizontally, but one of the important properties of internal waves is if the fluid is stratified continuously from top to bottom, you also have vertical propagation. Okay, but everything I'll talk about today is horizontal propagation. So these leading waves, as I mentioned, they're solitary waves. And they're, as you are all aware, waves of permanent form. Here is a echo sound image of solitary waves, mode 1 waves in the ocean. So this is just an acoustic image sending down sound waves from the surface, right? They're reflecting off particles in the water, could be phytoplankton, fish, but also turbulent streaks in this case. And here you can see sort of train of 4 internal solitary waves, mode 1 waves, and they're propagating to the right. So these waves are extremely common on the continental shelves of the world's oceans. And they're very important for a number of reasons because, they're very energetic waves and they transport things large distances. You can see the surface manifestations of these waves in satellite images or space shuttle photographs. So here is an example off the coast of Vietnam. So you can see these bands on the surface of the ocean, right? And these are the surface manifestations of large internal solitary waves. So these waves have large currents associated with them that modify the surface wave field, and that gives rise to these dark and light bands on the surface of the ocean. And these, so here we're in the, I guess the western side of the South China Sea, and that's the home to the world's largest observed internal solitary waves that have amplitudes of, about 200 meters in extreme cases. So very, very large waves. Okay, so I'm going to talk about the governing equations for a bit. So first of all, we've got the momentum equation. So it's just density times acceleration of a fluid particle equals the total force per unit volume. Okay, and now I'm going to make an important approximation to this equation called the Boussinesq approximation. So the density of water in the ocean varies by a few percent from a mean value of about 1,030 kilograms per cubic meter. So I'm going to set rho, the density of the fluid, to be rho naught times 1 plus rho tilde, where rho naught is, say, the reference density, say 1,030, and rho tilde then is much smaller than 1. And that gives the variations of rho about rho naught. Rho tilde is dimensionless, and because of the way it's been defined, it can generally take positive and negative values. So later on, I'll show some plots of the density field, and it'll show negative values, and this is why. So the Boussinesq approximation is to approximate rho times du by dt by rho naught times du by dt. Now, the pressure I'm going to split into a constant P naught, could be atmospheric pressure, for example, minus rho naught gz. And this is the pressure that's in hydrostatic balance with the reference density rho naught, and then plus a rho naught P tilde. So this P tilde then does not have dimensions of pressure anymore. But when I make this substitution, then the terms on the right-hand side of the momentum equation, I've got minus grad P minus rho g k hat, right? I can expand, so the minus grad P gives me these first two terms, right? And rho g k hat, I've got rho naught 1 plus rho tilde k hat. And the first and third term in this equation cancels out, and so I'm left with rho naught grad P tilde minus rho naught rho tilde k hat. And now every term in my equation, right, here's the left-hand side again, has this factor rho naught, which I'll now factor out. So here are the final equations that I'll be dealing with. So here, rho is dimensionless, P is being scaled by the reference density rho naught. So I've got two components of the momentum equation, a density equation, and I'm going to assume that the flow is incompressible, so I've got incompressibility. Okay, so the DJL equation. This set of equations has waves of permanent form, so exact solutions for waves propagating horizontally, and they have, so there are some necessary conditions to derive or to find these waves of permanent form. There has to be no viscosity and diffusion. There has to be no rotation. So I've neglected the effects of the Earth's rotation, and that's necessary to get fully nonlinear solitary wave solutions of the full nonlinear equations. And you also need a rigid lid. The Boussinesq approximation is a simplifying assumption, so it's not necessary. Basically, so waves of permanent form. I'm going to look for a wave that travels without changing shape. Here I'm again using sort of a two-layer fluid, or a fluid with a very thin pycnocline. And if you pick some point xz, okay, there's the fluid particle at the point xz comes from some undisturbed height z minus eta. So eta is the vertical displacement of the fluid particle. Now, if you go into a reference frame moving with the wave, the flow is steady. You can have a background sheared current. So U of Z would be some background current in the horizontal direction. C then is the unknown propagation speed of the wave. Okay, so if I go into this reference frame, I've got a background current like this. I've got my wave shape, I've got my vertical displacement eta. And you can derive an equation for eta for waves of permanent form. So here it is. So here, and I've just realized, so n squared, this is the derivative. Basically, it's minus gravity times the derivative of the background density field. So here, n squared is a function of z minus eta. The background current U bar is a function of z minus eta. And so here's where the nonlinearity in this equation comes from. So it's a nonlinear elliptic eigenvalue problem. Okay, the eigenvalue is the propagation speed c. Okay, and you want to find solutions of this equation satisfying eta is 0 at the top and bottom, because you've got a rigid lid, no vertical displacement of the top and bottom boundaries. And then for a solitary wave solution, I want eta to go to 0 as x goes to plus or minus infinity. Okay, you can also construct periodic solutions like conoidal solutions of the KdV equation. So the DJL equation only gives waves of permanent form, so no evolution of waveforms, but it is a useful comparison for solitary wave solutions of the KdV and the Gardner equations, and has been used to model observed waves in the ocean. So here's an example of an internal solitary wave solution of the DJL equation. So on the left-hand side, I've got some stratification rho of Z. The right-hand side, I've got some background current U of Z. And the middle, the black curves are the density contours. So this is my internal solitary wave. It's a wave of elevation in this case. And the colors indicate the horizontal currents associated with the wave. Now, without a background current, so if U is Z, for this stratification, the solitary wave would be a wave of depression, but in the presence of this particular background current, solitary waves are waves of elevation. Okay, so the Gardner equation. The DJL equation, as I mentioned, gives you waves of permanent form, but it gives nothing, right? It can't be used to describe the evolution of waves. You can't look at the interaction of waves. You can't look at how some initial waveform, steepens and disperses into a train of waves. So weakly nonlinear wave equations are very useful for doing that, for studying the evolution of waves. The Gardner equation then describes the evolution of weakly nonlinear, so small amplitude waves that are long. Okay, so weak nonlinearity, weak dispersion. So I'm going to say a bit about the derivation of the Gardner equation for internal gravity waves. So in this derivation, I'm going to assume that the background state consists of a fluid at rest, and I've got a density stable stratification rho bar of Z. So the buoyancy of Brunt-Weiselhoff frequency n is n squared is equal to minus g d rho bar by dz. So for stable stratification, the density must decrease with height. D rho bar by dz is negative. So minus g times d rho bar by dz is greater than or equal to 0. You'll often see this defined with division by reference density rho naught, but because I've made the Boussinesq equation or approximation, because I've scaled my density, made it non-dimensionless, I've already divided by rho naught, so it doesn't appear here. So I'm going to let B be G times rho prime. This is my density perturbation. So I'm going to take rho as, so I'm going to perturb it. So rho is rho bar plus rho prime, density perturbation. And then I take the curl of the momentum equations. I get the vorticity equation. And then here's the density equation. And this is in terms of the stream function, psi. So UW is psi z minus psi x. And here J is the Jacobian. So on the left-hand side, the n squared of z, this comes from the background stratification. And on the right-hand side, psi and b, they're both perturbation quantities. Okay, so boundary conditions, psi and b will be 0 at the top and bottom boundaries. Okay, so I'm going to non-dimensionalize. So the only important thing here is that both psi and b are scaled by a small amplitude parameter epsilon. Okay, so I do that, and here are my governing equations now. So left-hand, these are the terms that were on the left before. The terms on the right-hand side, you can now see I've got these parameters. So I've got a small amplitude parameter epsilon here, here, and over here. And I've got another parameter mu, which is the square of the vertical length scale over the horizontal length scale. And that appears here and here. So the KdV and Gardner equations are for small amplitude long waves. So waves for which epsilon is very small and mu is very small. Okay, so we can look for solutions in terms of a perturbation expansion. So here's my expansion in powers of epsilon. I've got order epsilon, epsilon squared, and mu here, and then higher order terms. Similarly for the buoyancy. So here I've got a function a, which is a function of x and t. Okay, so that will give the horizontal and temporal variation of the wave, right? And I've got various vertical structure functions, so phi of z, phi 10 z, phi 20, phi 01, etc. And then correspondingly for the buoyancy or density field. So to order epsilon squared and mu, the function a of xt is given by the Gardner equation. So here it is. I've got my small parameters epsilon, epsilon squared, and mu. and then coefficients c. So this is the linear long wave propagation speed, and then the quadratic coefficient alpha, cubic coefficient alpha 1, and the dispersive coefficient beta. So the vertical structure functions. So the leading order vertical structure function phi, so that's the function that appears in the first term in the expansion for the stream function, and then multiplying by n squared also for the density, is given by this linear eigenvalue problem. So I've got L of phi, so L is defined to be this operator, so second derivative plus n squared over c squared. Remember, n squared is a function of z. So acting on phi is 0, and my top and bottom boundary conditions. Now going to order epsilon, the vertical structure function phi10 is given by L of phi10 is equal to some non-zero stuff, which involves this coefficient alpha. So this is the quadratic coefficient, and again, these homogeneous boundary conditions. Okay, so this is an inhomogeneous version of the equation for phi. Okay, so we've picked C so that this equation has a solution. So L of phi is 0 for a particular value of C. Here I've got an inhomogeneous version of this equation. So I can only find solutions satisfying these boundary conditions provided alpha satisfies a particular condition. So that's a solvability condition. It determines the value of alpha. And it determines alpha in terms of integrals involving phi, the leading order vertical structure function. So here I've got the integral of phi cubed or phi prime cubed, in the denominator, the integral of phi prime squared. So similarly for beta. So beta, you can see you've got the integral of phi squared over the integral of phi prime squared, so it's always positive. But alpha, because I've got phi prime cubed here, it can be positive or negative. The cubic coefficient is also given in terms of, the ratio of two integrals. It involves phi and phi10. It can also have either sign, but it turns out it's not uniquely determined. And the reason is going back to these problems. So here's again, the equation for phi10. So L of phi10 is equal to this. Well, if I find any solution, say phi10 star, then I can add an arbitrary multiple of the homogeneous problem, which is phi. So I find any particular solution phi10, I can add a multiple of phi, the homogeneous solution, and I get another solution. Well, then I go back to my expression for alpha 1. Well, if I add a multiple of phi to phi10, I'm going to change the value of alpha 1. So alpha 1 is, say, alpha 1 star determined by some extra condition, plus gamma 1, 0 times alpha. So the cubic coefficient in the Gardner equation is not uniquely determined. Okay, and that is a reflection of the fact that, so here it's the Gardner equation again, and eta is, I'm using eta now instead of A. Well, the function that I'm solving for, so eta, you can have, choose it in different ways. So you can have different physical interpretations. So for example, it could be the current, the surface current of the wave. It could be the bottom current of the wave. It could be the displacement of, the pycnocline at the center of the water column, or the displacement of the pycnocline, a third of the way up, or so the isopycnal a third of the way up, et cetera. So there are different physical interpretations for eta, and if you make different choices for that physical interpretation, you will change the value of alpha 1. Well, the sign of alpha 1 is very important. So here's the Gardner equation. So as I've already pointed out, beta is always positive, and assuming alpha and alpha 1 are non-zero, then we can scale this equation to put it into one of the following two forms. So if alpha 1 is greater than 0, I get the Gardner plus equation, right? So here the coefficient of the cubic term is positive. And if alpha 1 is less than 0, I can scale it to look like this. The only difference is the sign of the cubic term. So I've got the Gardner plus, Gardner minus, and importantly, the coefficient of the quadratic nonlinear term and the dispersive term are both positive here. So the sign of alpha 1 determines whether the waves are modeled by Gardner plus or Gardner minus. And these two equations have very different properties, as many of you are no doubt aware. So if we go back to the KdV equation where we only have quadratic nonlinearity, here we've got solitary wave solutions with following properties. So there's a single polarity. There are waves of elevation if alpha is positive, there are waves of depression if alpha is negative, and that's the only choice. The larger the wave, the faster it propagates and the narrower it is. There's no amplitude limitation, although of course physically, if you've got internal waves in a fluid that's 100 meters deep, well, you can't have waves that are more than 100 meters in amplitude. For the Gardner equation, it's a richer sort of behavior. So first of all, so now I've got quadratic nonlinear, the quadratic coefficient alpha and the cubic coefficient alpha 1. Suppose alpha 1 is positive. Okay, so the cubic coefficient is positive. If we look in the upper right quadrant here, I've got positive alpha 1. So both coefficients are positive. So the KdV equation would say I've got waves of elevation only, unlimited amplitude. And the Gardner equation, I again get waves with any amplitude, with any positive amplitude. And no bound, so no bound on the amplitude. But there's a completely new branch of solution. There are now waves of depression. And these waves of depression have a minimum amplitude, but no maximum amplitude. Sticking with alpha 1 or alpha greater than 0, if I now make alpha 1 negative, so now I'm down here, I find I only have the waves of elevation that KdV equation would predict, but now there's an amplitude limitation. So we get these flat crested waves. So now as the waves get larger, initially they get narrower as KdV predicts, but then they asymptote some maximum amplitude, and as you put more energy into the waves, they just get wider and wider and become flat crested. So if I change the sign of alpha, right, so I just flip everything over. So if alpha is negative and alpha 1 is positive, I now have waves of depression for any amplitude, waves of elevation with some minimum amplitude. So here are some examples, example DJL solutions. So again, these are solutions of the full nonlinear equations. And here I'm using a 3-layer stratification. So for a 2-layer stratification, you can show that alpha 1 is always negative. For a 2-layer stratification, you've only got one of these two cases. So to get waves of more than one polarity, you need a more complicated stratification. So here's a symmetric 3-layer stratification. And I've got waves of depression and waves of elevation, as the Gardner equation would predict. And the waves of elevation and depression, however, do have limiting amplitudes. So we're in, say, this regime here, but instead of having, arbitrarily large amplitudes, the amplitudes are limited, and so you get waves that look like this. But now you've got waves of elevation like this, waves of depression like that, but with a minimum amplitude. And here's an observation of a flat crested wave on the New Jersey shelf. So one of the points here is that for internal solitary waves in the ocean, they're very often large enough that you really need higher order nonlinearity. The KdV equation is not enough. Okay, so here many of you will have seen things like this. Here's an analytic 2-soliton solution of the Gardner equation. So I've got two waves of opposite polarity, right, in this case, right? Here's the wave of elevation can have any amplitude. The wave of depression, there's a minimum possible amplitude, and this one's close to it. So this smaller, much smaller wave of elevation propagates faster than the much larger wave of depression. And, they interact and, they reappear with their original amplitudes. Okay, now I'm going to show some simulations of the interaction of DJL solitary waves. So here I'm using a numerical code that solves the full nonlinear equation. The simulation is being initialized with solutions of the DJL equation. Here I've got, well, two waves of different amplitudes, so they have different propagation speeds. These waves are propagating to the left through the fluid, so as the orange arrows indicate, and I'm in a reference frame moving with the average propagation speed of the waves. So in this reference frame, the larger wave is going to propagate to the left. The smaller wave you'll see going to the right. So they'll interact at roughly the center of the frame. Now, the density, the contours here show the density contours. So it's a very thick two-layer fluid. But there is also a background current indicated over here. So the background current is 0 down below, and then it increases as you go up towards the surface. So one of the important results of this is that the larger wave in this case has what's called a trapped core. So if we're in a reference frame moving with this wave, so the flow is steady, right? The density contours would be streamlines. And if we drew streamlines up here where there's no stratification, you'd have closed streamlines. In other words, there's a blob of fluid that's trapped with the wave and propagating with the wave. And I'll show that partway into the animation when I add some particles. Okay, so here I've added some particles, and some of the particles just get swept out the back, and some of the particles that were inside the core are trapped in the core. And they move with the core, so they move with the wave. So here the waves interact, and off they go. So you can see that the interaction is very much as predicted by the KdV or the Gardner equation, right? After the interaction, the large wave has almost the same amplitude as the initial large wave. Similarly for the small wave, but there is, as you can see here, some very small amplitude waves being shed, okay? So they're solitary waves, they're not solitons. They interact, they do change amplitude slightly, and they do radiate some small amplitude waves, but the radiation is very small, so they're very close to solitons. Okay, so here's some other examples with a three-layer stratification. So two hyperbolic tangent profiles, right? Delta rho 1, delta rho 2 give the density change across the two pycnoclines, right, which are centered at Z1 and Z2, and they've got thicknesses D1 and D2. So here is sample stratification. So I have an upper pycnocline that's a bit weaker than the lower pycnocline, and it's also closer to the upper boundary than the lower pycnocline is to the lower boundary. So for a three-layer stratification, if the pycnoclines are close to the boundaries, so if one's close to the upper boundary and one's close to the upper boundary, then the cubic coefficient will be positive. And I see I've got a typo here. So actually alpha 1 is greater than 0. Okay, so the KdV equation will predict solitary waves of elevation, and the Gardner equation will predict solitary waves of depression with minimum amplitude. Okay, so KdV equation says waves of elevation. So here is the interaction of two waves with the KdV polarity. So again, in a moving reference frame. Okay, so the larger one is catching up with the smaller one, but we're moving with their average propagation speed. So they're both sort of propagating towards 0. Okay, the waves interact. And again, there is some very, very tiny waves are radiated. Okay, so they interact very much like KdV or Gardner solitary waves. Okay, now here are two waves of polarity opposite to that of the KdV solitary waves. Okay, so I've got small wave, and this is very close to the minimum amplitude, okay? And then a larger wave, which propagates faster. So this one is going to catch up to this one. So what's different here is you can see there's significant radiation of waves. Okay, so the interaction is different in that sense. Okay, it's much further removed from being a KdV type behavior or from being solitons. And here's the interaction of two waves of opposite polarity. Okay, so lots of radiated waves. Okay, so very different then. Okay, so finally, in terms of the Gardner equation, and maybe I'll say a little bit about breathers. So many of you are aware. So the Gardner Plus has also a completely new type of solution called breathers. Okay, and so here's an example of the interaction of three breathers, right? So they interact and they reemerge with their initial identities. Well, do breathers exist in the full nonlinear set of equations? So here I've done some numerical simulations, and so I've initialized the code with analytic breathers. Okay, so they're weakly nonlinear breathers that have been used to initialize the fully nonlinear equations. Okay, so because they're not exact solutions of the full equations, they're going to radiate a lot of waves. And again, these waves, so my breathers are propagating to the left, so you're going to see lots of waves being swept to the right as they adjust. And they do interact and they do seem to reemerge, although not with their original amplitudes. Okay, so breathers do seem to exist, or almost breathers at least seem to exist in the full nonlinear equations. Here's a different example showing the generation of a breather. So now I've got a steady current flowing over this tiny bump. So it's a three-layer stratification. It's symmetric and the pycnoclines are far enough away from the mid-depth that the cubic coefficient is positive. Okay, so flow from left to right passing over this bump. And you can see downstream of the bump, some very large waves are generated. So much larger than the bump. And after a long time, we'll see a breather emerge and propagate upstream. Okay, so here it goes. Okay. So there's a breather going upstream, and then after a while, a second one emerges, and you get a sequence of them going upstream. Okay, so here, I guess maybe a more clearer example than the previous case. So here's a similar example, but now the flow is over a depression. Okay, much faster oscillations in this case. I've sped things up. But now, okay, a breather-like wave propagates upstream, and you can see that it seems to be more flat-crested. So here's a much longer one going upstream. So it looks like a possible breather. It's flat-crested, so it's got limiting amplitude. So I've tried various currents and so on, and I mean, can't get anything larger than this. Okay, so I'll just finish up with just a few things about the NLS equation. So, and again, most of you are aware of how this works. So now I'm going to look for solutions. So here's my stream function. I'm going to look for solutions in the form of, so I've got some oscillations, some of my carrier waves with wave number k and frequency sigma. I've got some vertical structure function, which would be the same as it was before. And I've got a slowly varying amplitude, so varying slowly in space and time. Okay, so after a lot of algebra, you get the NLS equation. So here, CG is the group velocity. So it's the d sigma by dk, sigma of k being the dispersion relation, right? Beta is a half times the derivative of the group velocity. Okay, and then nu is some nonlinear coefficient, very complicated expression. Okay, so the dispersive coefficient and the nonlinear coefficient nu can have either sign. Okay, and so as I'm sure probably you're all aware, there are really two scaled versions of this equation. So for example, if both those coefficients, if beta and nu are both positive, you get NLS plus, right? If they've got opposite sign, you've got NLS minus, okay? Or if both of the coefficients are negative, you get NLS plus again, sorry. Okay, well, both NLS plus and NLS minus are possible for internal waves. So here's an example that's really the anomaly, constant n. So up here, I plotted the dispersive coefficient for mode 1 waves, mode 2 and mode 3, right? So if you remember back at the beginning, mode 1, they're the waves that are always, the vertical displacements are in the same direction. Mode 2, the vertical displacements change sign once. Mode 3, they change sign twice. So the dispersive coefficient is always less than 0, right? So you can prove this analytically. The nonlinear coefficient for mode n waves changes sign at a particular value of k. Okay, so for small values of k, it's negative, right? And then when k passes this threshold, which is proportional to the mode number n, right, nu changes sign. Okay, so I've got NLS plus for long waves, I've got NLS minus for short waves. Okay, so NLS plus for long waves, so you got solitons, modulational instability, whereas for short waves, right, it's modulationally stable. Okay, so very different. And this is completely the opposite to the case for surface gravity waves. If I consider a single pycnocline, so these 5 curves integrate 5 different 2-layer stratifications, pycnocline at different depths. Over here, I plotted n squared, so that's just minus the derivative of the density. Well, here I'm plotting C and CG, so the phase speed and the group velocity. Here I'm plotting the dispersive coefficient. Dispersive coefficient is always less than 0. Here is the nonlinear coefficient, and there are just 2 plots with different ranges of k values. So here k between 0 and 5, here between 0 and 2. So now the nonlinear coefficient is positive for long waves and negative for short waves. So the opposite of what it was for n constant. Okay, so now it's short waves that are unstable. So a more interesting example. It's a 2-layer stratification, but instead of having 2 layers of constant density, I've got 2 layers with constant buoyancy frequency. Okay, so I've got a lower layer with small buoyancy frequency, and then an upper layer with a larger buoyancy frequency. And now things are a lot richer. So here the upper panel shows the dispersion curves. So this is frequency as a function of wave number k. And down below is the phase speed and the group velocity. So the group velocity is maybe what's interesting. So the phase speed, it decreases monotonically with k, right? As the waves get shorter and shorter, right? Propagation, phase speed goes down. But the group velocity, which is the derivative of the frequency with respect to k, is given by the dash curves. And you can see it's not decaying monotonically. Okay, so here for the mode 1 wave, the red dash curve, it is decaying monotonically, but for the mode 2 wave, well, it decays and then it increases and actually becomes larger than the mode 1. Similarly, mode 3, right, it decays and then it increases. Well, the dispersive coefficient in the NLS equation is the derivative of the group velocity with respect to k, so you can see from here the dispersion coefficient is going to change sign. So here's the dispersion coefficient as a function of the wave number k. For mode 1 waves, it's always negative, but for mode 2 waves, well, it's negative and then it's positive and then it's negative, right? Mode 3, similarly, negative, positive, negative. And if we look at the nonlinear coefficient, there are also many changes in sign, right? So red is for the mode 1 waves. So it's negative initially, but then it becomes negative. Sorry, positive initially, then it becomes negative, and then it's positive, and then it's negative, and then it's positive, and then it alternates sign. Okay. So I think that's all I've got here. So I just wanted to make the point here, I suppose, that there's a very rich behavior of nonlinear waves, in nonlinear internal waves, and a 2-layer fluid is really not well, a 2-layer fluid with constant density in each layer is not a particularly interesting stratification, right? There's an infinite range of choices for stratifications, and there are lots of stratifications with really, really rich, interesting behavior. And I'll stop there.